Couchbase and how you create indexes and manage that process. This talk will start with some of the more runtime oriented or kind of deployment oriented, so that you understand how the system works and how the indexes are maintained and it all works across a cluster, etc. And then we're going to dive into examples of actual index definitions and how you would query it, and then some design patterns so you know what you can use it for. So some of the more developer-focused stuff is going to be toward the end with a little bit more inside architecture stuff at the beginning. So we're going to talk about some basics so you'll have a sense of the big picture, and then we're going to dive into the life cycle so that you'll understand the difference between defining an index, when the server actually builds the index, and then when you run your queries. We'll cover a little bit of the replication strategy for high availability of indexes, and then start talking about some basic patterns like primary and secondary indexes, some performance considerations, how to best use views to get the most performance, and then some more advanced patterns like how to do statistical rollups. So hopefully this is the content you're looking for. After sitting through this webinar, you should be in the position to sit down with a copy of Couchbase Server 2.0 and the example databases that it ships with, or your own data, and at least write some queries that make you feel like you can see inside your data. So just to start with, basic overview of what is JSON. This is our primary document storage format. It's a standard that's based on JavaScript, but it's been adopted by pretty much every programming language as a serialization format. So it's got some basic types, like strings and numbers and booleans, arrays, and objects. And so you can structure pretty much anything you're doing in your application to be serialized as JSON and then stored in Couchbase under an identifier key. So this primary storage path is a key value store, which means that in order to load a document, you've got to know the ID of the original document. That is the high-performance read and write path, but it's you're constrained by having to read and write from that key. So this is where the query engine really comes in. Queries are what allow you to find documents if you don't already know their identifier. So if you're, in my previous webinar last week, we talked about performance constraints around interacting with this key value API and how you want to push the hot path of your application to use it as much as possible. And then we hinted somewhat at how the query capabilities, they're essentially really flexible, allowing you to architect your application around key value access for the hot path, and then running queries to pull in, sort of other views of the data, maybe for secondary features or parts of the application where the user's not going to be quite as sensitive to latency. So views are the primary method you query a Couchbase cluster. Essentially, it allows you to take your original documents represented at the top half of the slide here and run them through a process that normalizes their structure into an index so that you can do lookups on those normalized fields. In the example we've got here, we've got 3 people, and they all have names, but only one of them has a city, and only 2 of them have salaries. So in the case of the document storage, the actual JSON for some of these users doesn't necessarily have like city equals null or salary equals null. It just plain leaves the field out. And so that's going to be really common with schemaless storage. You'll store for each record what's relevant for that record. And then at index definition time, you'll essentially normalize that so that your application, when it's reading these queries, doesn't have to deal with variability in the data set. So on the top half, we've got this variable, potentially messy set of documents, and on the bottom half, we have well-ordered and sorted, essentially table, logical table structure that you can do lookups into in a fairly scalable way. So how does that work in the runtime? You define what's essentially a materialized view, and that's the definition phase. It builds the index, and then you query across that index. So the kinds of use cases we can support are a primary index, where you're looking up documents by the ID, and this is especially useful if your IDs have some structure to them and you want to do range queries across your IDs. Probably the most common use case is a secondary index, so finding users by email address or last name or city and state, that kind of lookup. And then you can do more complex things and aggregations. And sort of the key to the complex indexes is that because you have this full expressive power of JavaScript to inspect the documents and decide what to index, you can drill into different fields on different record types, or if you have old and new versions of the same record type coexisting in a bucket, you can normalize those in the indexer. So we'll talk about all those patterns toward the end. Sort of next up, we're going to talk about the runtime stuff. So that's where you'll understand what we really mean by eventually indexed and eventually consistent. So the last point, and this is a good high-level point to understand. So we use MapReduce, which is made famous by the Google and Hadoop implementation. But MapReduce itself is more general. And so if you look at the way that Couchbase MapReduce works, it's a different interpretation of sort of the same underlying mathematics that Google and Hadoop use. The big difference is that our MapReduce is incremental. So it really is building indexes that you can query rather than, in Hadoop, the MapReduce is more like a batch job. It's more like running a process over your data to come up with, a derived data set that you can then potentially load into something else, like Couchbase for real-time access. So you can think of it essentially as a processing chain that's built into the database that allows you to make these transformations on your documents and keep the indexes up to date. And if you want to relate it to something simple, it's a lot like, if you're familiar with relational databases, defining an index on a relational table. The big difference being that it's optimized for schemaless or varying data structures instead of requiring that the structures fit into a table in the first place. So let's look at this view lifecycle. There are these three main steps: the definition, the build phase, and the query phase. So before we can show that, we'll show just sort of the bird's eye view of what's happening. Here is a representation of Couchbase Server with two buckets, both with JSON documents in it. And then the first bucket has two view groups, and the second bucket has one view group. So that's what a design document is, essentially. And from a runtime standpoint, what's important for you, the developer, to know is that all the views that are within a given design document are processed together. And so that allows us to get some optimizations as far as handing off things to the various processing steps. And we can go into detail on that if somebody has questions and really wants to understand what some of those optimizations are. But the important part for you as a developer is that all the views in a given design document are processed together. And so, for instance, it makes sense to group them by kind of their access characteristics. So if you have an application that has two main user groups, you've got sort of your customers, and then you have internal managers who want to run some analytic queries. That may be two design documents, one for the customers and one to use internally. And the real benefit to that is that it makes it easier to reason about and more fun to work with. So if you have a design document and you need to change one of the view definitions, it's nice to be able to change that. Like, let's say your managers are always updating what they care about and they want new reports all the time. Since those in this scenario are in their own design document, you can change those all the time without impacting the end user visible queries. So that's probably the most pragmatic reason to to know or care about this design document grouping, is that it allows you to, decide exactly, which changes to your schema are going to affect which index structures, and kind of isolate, fast-moving parts of your application from parts of your application that are relatively stable. So here let's look at the data flow so you can see what we mean by eventually indexed and eventually consistent. In this picture, we've got your app server at the top of the diagram, and at the bottom is sort of a schematic of Couchbase server. So we're going to move the document to Couchbase server. This corresponds to a set operation, and that's going to land in memory. The very first thing that happens once that document is committed to the cache layer is that, because we need redundancy and reliability, right? Your data is important to you, so you don't want it just in one place. We send it out to other nodes in the cluster for redundancy, and at the same time we schedule it to be written to disk. So now that document is on these two queues. One is for the disk and the other is for replication. The replication queue is going to move much faster because that's writing to memory on another node, and then the disk queue will drain eventually. Ideally, if your cluster is sized correctly, the disk queue length is going to be measured in seconds, if not shorter. But under heavy load or unexpected traffic spikes, the disk queue can grow longer and then recover when the load goes back to normal. So that is going to impact how long it takes before your data shows up in the view engine. Because as we see in the diagram, the view engine is driven by disk updates. So once it's been written to disk, then the view engine can process the document and insert it into the index. One of the reasons we chose that approach rather than building the indexes directly off of the managed caching layer is that disk write queue is a deduplicating queue. So if your app server is hitting the same document thousands of times a second, it's still only going to write out to disk once a second or so. And that means that there's much less churn in the storage layer and much less churn in the view layer. So you don't need quite, it saves you on needing more storage, hard drive bandwidth than you otherwise would. So having the view indexes after that deduplication layer is, one of the architectural choices we made in Couchbase because of the scale and performance requirements that our customers have. So that was the story on a single node. Now we want to look at the sort of the same story, but from the perspective of a full cluster. So what we've got here is your app servers at the top of the screen and the Couchbase servers at the bottom, and the documents are spread evenly across the cluster. So the first step is to define a view. So you can see that source code in the upper right-hand corner of the screen. I would, don't worry about understanding that completely right now. We'll get into the details on it toward the end. But the idea is that definition is sent out to the indexers on all the cluster nodes, and each node maintains its own index of active data and optionally a parallel index of replica data for high availability. So now when we query, the query is scattered to all the active indexes and merged by one of the Couchbase server tiers and sent back to the app server. So this means that all your queries are hitting all the nodes and having access to all the data, but the app server only really has to interact with a single point in the cluster. So after that is, after the query is scattered out to all the nodes, then the results are gathered and sent back to the app server. So let's define a simple index. This is that code you saw in the upper right-hand corner. And it's equivalent roughly to the SQL statement that you see at the top of the screen. So in a relational database, you may create an index and give it a name and a column on a particular table that you want to index. In this case, we're indexing the breweries table on the city column. And how that looks in Couchbase is a little bit different. The biggest difference is because Couchbase keeps all the documents in one bucket rather than splitting them out by tables. What we do first in the view is filter it so we're only interested in brewery documents. So that's what that line 2 in this JavaScript code does, is it makes sure that we're dealing with a brewery, and then it also makes sure that that brewery actually has the city field. If we left out the doc.city there in the if clause, then any breweries that had incomplete information would all get indexed together under the key null. So there are other times when you're going to want to be more guarded with your if clause, and we'll talk about that later. But for a simple index like this, it's usually sufficient to just make sure that the field you care about is there. So now that we've defined this index, we're going to build it. So we take the definition and send it out to every node where it builds the index based on the data that's stored. And that's, again, done in an eventually consistent way. So the index will be up to date eventually. And there are ways to query it, to ask it to bring itself up to date before it gives you query results, depending on your use case and your consistency requirements. So again, these indexes are disk-based, and it's going to be, disk-type speeds rather than RAM speeds. So while we may be able to do 100,000 operations per second on a key doing CRUD operations with a view, it's not going to be quite that fast. It's, it makes up for it in terms of power and that you're getting back multiple rows in a single response. But for your hot path, you're still going to want to stick to the memory-based CRUD operations. So the build phase keeps those views up to date and builds a distributed B-tree index across the cluster. Here's a logical representation of it. The goal of this kind of index structure is to provide the ability to drill down to a particular key and then sort of iterate over the keys that come after it in a range, and to do that efficiently with the least amount of hops across the disk as possible. So if you really want to get into understanding that stuff, the Wikipedia article on B-trees is a great place to start. So now the query phase is where everything that's dynamic comes in. So you have this index that you've defined, and the cluster has built it, and then you're going to throw query parameters to the server, and it'll apply those to the index to find the results to show you. In the case of a secondary index, that's pretty simple. You're saying, find me all the users with city equal to Mountain View. And then for the reduced indexes, it gets to be a little bit more interesting because what you can give it is a full range and then ask it to run the aggregation function over that range. So in this case, we're just finding all the cities that start with J, and in our example data set, it's just Juneau, Alaska. So that's what we see as a result. And if there were new cities that start with J on any of the cluster members, those would show up in the result set too. So as I mentioned before, the views are grouped by a design document, and that's also, you can look in the database and see the design documents and see how the definitions are stored, although for the most part, you'll be happy using either the client library SDKs or the admin UI to define views. You don't really need to worry about what a design document actually looks like, just the fact that as they're, that they're run as a unit. So, one little piece of detail here is that we want the view results to be as up-to-date as possible for the end user when they query, so that they're seeing as much of a consistent snapshot as we can make available. But there's a bunch of other sort of design trade-offs in that space. So if we were extremely aggressive and updated the indexes on every insert, then we would be in a position where that index structures on disk become really bloated and need to be compacted frequently, or else they'd be slow to access. So it's configurable, but the trade-off we've decided on for now is that every 3 seconds or so, if there have been a lot of writes and no queries, then we're going to update that index. So the index will never be more than 3 seconds out of date, but you can configure that both, sort of globally and also on a per operation basis. We'll talk more about those consistency models in a little bit, but the key is that, by default, we'll give you the fastest access we can, even if it's to some data that's 3 seconds old. But if you need access to data, like if you want to read your own writes in a sort of transactional fashion, there are patterns that allow you to do that. So here's kind of the one side of those patterns is every time you read a view, it's either going to give the index that already exists or bring the index up to date. So stale equals update after, which is the default. What that does is it reads the existing index data structure and then returns those results to you, but also schedules an index update to happen. So if you are getting lots of read queries off your views, then your views are going to stay more up to date than that 3 second window that I talked about previously, if you're using update after. Stale equals OK will never trigger an update, and so in this case, it's likely going to be that 3 second rule that kicks in and defines the consistency window of your indexes. Stale equals false is the most consistent option, and what that means is that the query will not return to the client until the index has been fully brought up to date with what's stored on disk. So that can take some time depending on how many updates have happened since the last time the index was updated. Now that alone isn't going to give you read your own writes kind of transactionality. If you need to read your own writes, you'll also need to do the writes with the observe option, which I talked about in the previous webinar, and it's in our documentation, but the gist of it is that if you flag the write with this observe flag, then it gets scheduled with priority to go to disk, and the SDK doesn't return from the write operation call until it's on disk. So if you do an observed write and then a stale equals false query, you'll see your own data in that view. So that's sort of the gist of a given index, but there's also replica indexes, which we use for high availability. So by default, we have these turned off, but people who need to fail over and have active view queries going all the time may want to run it, although there's double the cost of disk I/O as far as the index throughput. So let's see, I've got a question here about queues, and so the question is about consistency, and perhaps I just answered it. So it's just to get the question out there because it's interesting. Let's say you're using one of these views to maintain a queue, and you want to run a query to say, like, find the entry with the greatest timestamp and do some work on it, and then tag it, the work's done. So in that case, you do need a strong consistency model, or else you're going to write something to the queue and then query the queue, and it'll look empty. And so you could either have your queue reader sort of understand that just because the queue is empty now doesn't mean it's going to be empty in the future, and or you could use that observe and stale equals false pattern to get a fully consistent write plus query experience. And if you do that, it is going to be at the cost of increased latency. We've tried our best to make it so that while that stale equals false and while that observe write is happening, it's not going to impact negatively other queries that are going on in the system, but it will take longer, right, for your full write to happen and the full index to happen than it would if you didn't care to wait for those events. So back to the replica indexes. So as I had in the diagram earlier, each Couchbase cluster node, maintains not only its active working set, but also the set that will be enabled in case of failover. And the gist of the replica index is that it's on-disk data structures maintained so that they're ready in case of failover. So when you do failover, you'll have essentially consistent query performance even on the replica node. Again, this is optional. Certain use cases will be fine with partial unavailability of some of the indexes for a short window after a failover. It really depends on a cost-benefit analysis that's going to be particular to each application. Another runtime characteristic that is maybe more operations focused than development, but important to know about, is that those on-disk data structures are always growing with each and every update to the view index. So what we do is we have an automatically scheduled job that cleans up those files to keep them from being too fragmented. Occasionally you'll see that reflected in your sort of active tasks on the cluster if you go look in the admin UI. And it can increase, it uses some disk I/O when that's happening. So it shouldn't impact your get and set CRUD operations, but it could potentially change the latency characteristics of view queries while compaction is running. So there's one other nuance, right, that you're going to want to know when you want to take this sort of stuff into production, and that's the difference between development and production views. So everything I've talked about applies to both of those. At the code level, at the low level with what's happening in the cluster, there's not really a difference between development and production, but what we've done is built some workflow on top of it to both help you update your views without incurring any downtime, and also to just help with the development process. So if you have terabytes and terabytes of data across tens of servers, and you create a new view definition and then query it, it's going to have to do some work before that query is, before that index is built and ready to query. And that's going to take time, and that's not that fun when you're just trying to iterate on some code to see if it's the right idea in the first place. So in development, we have development views that run on a subset of the data and return results to new view definitions very quickly. So typically they're going to run on just the data that's resident on one particular node, or maybe even a subset of a node, depending on your cluster layout. The important thing is that they return fast and give you the chance to see whether or not there were any bugs in your view implementation. Once you're happy with your view, you click Publish in the admin UI, and it's promoted to production. So what that means is that first the index is built out across the entire cluster, and then we flip a bit to make it public. So if you have an index, called by city, and you update the code so that it includes, not only breweries but also coffee shops, and you hit promote to production, what it'll do is build that index up and then swap it out with the existing index, so you're not left with a window where you don't have an index to answer those queries. And that's a big help. Without that, you would be in a position where you could potentially have some downtime for changing index definitions. But instead, we protect you there and make sure that you're going to have your views are always available. So let's look at some indexes. Here's an example document. This is from our beer database. So the beer has a name. It's got an alcohol percentage. It's got a type. It's got a timestamp, and some other fields. So we're going to create a primary index. This is the most basic kind of index, and it would be useful mostly if you're doing range queries over the document ID. So if you just want to look up a document by its ID, use a get operation, and that's going to read it out of memory and give you, the highest performance with the least impact on the cluster resources. But if you want to find all the IDs that share a common prefix, then you'll want to build a view like this and run a range query in order to find the common prefix. So we've got these two arguments to the function, the document and the metadata. And the metadata is actually where the ID, in this case, it's things like 110F which is the IDs for these brewery documents and beer documents. And so we're taking that meta and extracting the ID from it and using it as the lookup key in the view. We can take that same approach, and you see we didn't change the code much at all, but instead of emitting the document ID, we're emitting the metadata, and or rather the document name. So that's just user data. That's something that we imported into this beer database. And now you can see the names of the beers and the names of the brewing companies are both being injected into that index. We could add a line of code at the top of that index definition that filters on just breweries or just beers if we wanted to only show the names of documents of a given type. But in this case, we're looking at any document that has a name so that we can sort them by name. So we can also be a little bit more specific. In this case, we're using the brewery ID, so something like this is probably useful for lookups inside your application. You've got a brewery, and now you want to find all the associated beers. So you can run this lookup, and it'll find all the beers with a given brewery. And we see, on the right-hand side, we have a value that we're using. We hadn't been doing that in the previous examples. So typically, if you're going to use the second argument of the emit function, what that does is it puts whatever you store there directly into the index data structure. So it's important that whatever you emit as a value be small. As those things get larger, you're going to have sort of an outsized performance hit. So if you put something very large in the value, it's going to be detrimental to performance. But small things like numbers or a small set of numbers or an important string, that's what it's there for. So in this case, the value is the ABV, the alcohol for that beer, and you can see that on the right-hand side. One other nuance to this screenshot, just to to finish up the story here, I've got a box around reduce equals false. This is a query parameter that you're going to use when you've defined a reduce function, but you're not interested in the aggregate results. You're interested in the underlying rows. So here we're running reduce equals false, and it means that it's basically pretending we didn't define a reduce function for the purposes of our query. So we can actually see the key and the value and the key and the value for everything that we emitted. In a minute, we'll see what happens when we use reduce. So there's that index definition again. We've got the brewery ID as the value, and the second or as the key, and then the second argument is the value, which is, in this case, the alcohol by volume. So, most of what you're doing most of the time, you're just going to be emitting keys, and your value is going to be null or empty, or sometimes like number 1 if you want to count some stuff. But generally, you can leave out the value and just work with keys, because you'll want to fetch the full document anyway once you get the result set back. So there's that result set again, the beers keyed by the brewery ID. So we'll drill in later and look at how we're going to do aggregations over the alcohol by volume on that view. But first, let's talk about some of the performance constraints that, and considerations you're going to want to have. So if you have, some views that are frequently used and other views that may be less frequently used, and especially if those other views are heavyweight compared to the more frequently used views, you're going to be happy if you split those into 2 different design documents, just because it gives you, another additional amount of administrative control over, whether or not to rebuild a given index or change a definition without impacting the other stuff that's happening. You don't want to have too many design documents, so don't go making like 20 design documents unless you have a really good reason to do that. Typically, you're better off having a design document with 10 views in it than having 10 design documents with 1 view. Yeah, another important thing to note is that, like, if you're given, you're sort of trying to decide whether I want to have 1 view that's really clever or 3 views that are each less clever and that have more of a special purpose job, rather than trying to make some generic view that is more general purpose, it's often better to make a collection of special purpose views. From a runtime and performance perspective, you're certainly not going to have a tax or a negative impact from splitting things out into multiple views. The actual sort of CPU time of executing the view code is negligible in terms of the overall performance profile. Most of it is about writing data out to the indexes, and 3 views that are distinct versus if you sort of merged them in code to be one view, it's going to be just as efficient to run the 3 views. So there are, it's possible to write a custom reduce function, but you're going to get much better performance with the built-in reduce functions. You're also, more likely not to, if you write a custom reduce function, the first couple times you do it, you may get some gotchas, just because, well, what I see is that folks who are familiar with Hadoop-style MapReduce will try to write Hadoop-style reduces, and it doesn't work. It's not designed for that. You need reduces that actually reduce. So I'll talk about some examples of that in a little bit. And then this last point is really important. If you were to, so I've got there, if the document has an ingredient, then emit the ingredient text. If I'd left out that guard clause, I was mentioning this earlier, if you leave that out, you're going to have a runtime exception in the view, because it'll try to find undefined .ingredient text on documents that don't have ingredients. And trying to find undefined .ingredient text is going to throw an exception, and it'll halt the processing of that document for all the views in your design document. So you can have a runtime exception in one view, cause the document to be missing from another view, unless you are careful to check for attribute existence. So that's, I guess I would consider that a known issue. We're working on cleaning that up, but in the short term, you just want to be careful that your view code can't throw runtime exceptions. And typically that's as simple as making sure that you're only interacting with data that actually exists. So as I mentioned before, you're much better off with small values and keys for that matter, because these go directly into the index data structure. So don't emit the whole document as the value. We see a lot of people out there, running emit doc.name, doc. And if you're doing that, you're going to bloat your storage. It's much better to emit doc.name, null, and then load the document via the get API or via a multi-get after the result set comes back. And actually, most of the client library SDKs support the include docs query parameter, which in their case, rather than loading the docs during the view query via the view API, what it does is it makes a regular view query, like you'd get back for emit doc.name, null here, right? So you get a list of all the names and the associated document IDs sorted by name. So that would be your result set, and the SDK will actually go and fetch those documents for you. So that's just another reason why you can probably afford to do, lightweight indexes and load the full data at, after you've run the query. So, as I mentioned before, if your document is missing a field but you don't throw a runtime exception, it'll just emit null. And so, like in this last view where we're filtering by players, if we had left that filter out, we might get just a whole bunch of unrelated documents all in the view, all under the key null. And that's, it's just not as lightweight or as efficient. You're indexing stuff you're not going to use. So do use document types or some other, constraint in an if clause to make sure that your index is really only indexing the stuff you care about. So here's, sort of a short list of some runtime, considerations. The more complex your code is, of course, if you've got a loop in your JavaScript, it's going to take a little bit longer for the CPU to manage it. I think that one is probably, you know, one of the least important ones. I've seen some massive JavaScript that, you know, is pretty expensive on the CPU, but as long as the result of that isn't a massive index, you know, if you're not emitting 50 keys for each document or something, then that's not really a cost you need to worry about. But if your view is emitting much more data than you're actually going to query, then you're going to be using a lot more storage and a lot more storage bandwidth than you otherwise would. So having lean indexes is probably the most important consideration. Again, if you run a replica index, it's going to essentially double your disk requirements. So be aware of that. You know, if you need high availability on indexes, it's a cost you've got to pay, and it'll show up as running a larger cluster. So if you have you know, more design documents, then you can start to run into some scheduling issues if you've got more than a handful of design documents. So again, sort of, I find that if I lay out my view groups and design documents in a way that's designed to be easy to think about, you know, like sort of put my developers first, other stuff falls out properly. You don't want to have a whole bunch of design documents. It's hard to reason about. So if you have a handful of design documents, then it's easy to reason about and easy for the cluster to manage. Compaction is going to use some CPU, but mostly I/O. And then probably the most visible thing you're going to get if you had been using Couchbase without views and then start using them heavily, if you are you know, running index-aware rebalances, which are turned on by default, then that means that we're always making a consistent query result available even during rebalance, but that can significantly slow down the amount of time it takes to do a rebalance. So if you're just adding a couple of nodes to an already large cluster, that might not be an issue, but if you have a small cluster and you want to make it into a large cluster, you may want to turn off indexing and then blow the cluster up and then turn indexing back on. Or rather just disable this index-aware rebalance, and that'll give you much faster rebalances. So if you're running views heavily, you're going to need some leftover RAM on the box. Like if you weren't using views, you might grant Couchbase the full quota to all the available RAM on your box. But if you want to have fast view responses, you're better off leaving some significant amount of RAM unused by your Couchbase, you know, memory cache buckets and available for the file system cache. So yeah, let's get into, you know, actually writing some queries here. So I talked earlier about reduces and how you can use them to do some aggregations. So this is that same view we saw before. We have the beers sorted by brewery, and then as the value, we're emitting the alcohol by volume. And what you'll see that's different from the previous query, previously we ran the query with reduce equals false. Now we're running the query with group equals true and reduce equals true. And so that means that that stats function that was just sort of sitting there being ignored previously comes into play. And you can see that in the result set. So here we have the key on the left corresponds to a brewery. So while each brewery may have lots of beers, it's only going to show up in this result set once because we've grouped by the key. So you can see that that very first key has a count of 8. The count of 8 comes out of the stats function, and it tells us there are 8 beers from that brewery. Now, the other numbers are really there to let us calculate things like the standard deviation of the value for that brewery. But one of the simpler calculations we can do is we can divide 54.6 by 8, and that'll give us the average alcohol by volume for all the beers made by that brewery. So yeah, it looks like from this set, those top 3 are actually pretty close, and that one at the bottom is, you know, maybe making lighter beers because they've got 5 of them and it only adds up to 22.8, so they're somewhere like, you know, 4 and 4.25 or something alcohol by volume, whereas some of the other breweries look like they're trending up in the 5 and 6 range. So that's just the average that you can pull out of those values, but you can also pull the standard deviation, and of course the count and the min and the max are already available there. There are 2 other built-in reduce functions, and they're essentially subsets of stats. So if you don't need everything stats is doing, you could run underscore count and it would just run the count for you. Or you could run underscore sum and it would just run the sum for you. So that's going to be slightly more lightweight. If all you need is those, then I would use those. But stats gives you those 2 values as well as what you need to calculate the standard deviation. So here's a zoom in on that. You can see there the reference to underscore count and underscore sum as well in the admin UI. So I mentioned briefly that what we're doing is grouping by brewery, and I just threw that off like an offhand remark, but it's really powerful, and we'll see some more power from that in a minute here. But what that does is it dynamically runs the aggregation on every value that has the same key. So you can see on the left that's a unique set of the keys, and then you're getting the stats for each key, for each unique key. So where this gets really powerful, and we'll see in a second, is when your keys are complex. So with a compound key, you can actually dynamically group with varying depths into the key. So if we had sort of like brewery and then type, right? So if this key was, instead of just a brewery ID, it was also, comma ale and comma porter and comma stout, then we would see with group level 1 exactly what we're seeing now. But with group level 2, we would be able to see that, this particular brewery has strong stouts and light porters, or vice versa. So we'll look at an example of that here in a second. With this time-based rollup, which is one of the most popular uses of that dynamic grouping capability. So here is a comment on beers. It doesn't really matter what the document is. What we're concerned about is the timestamp. So we've got a timestamp field on this document. The format of that timestamp is not great, right? You could have a better format, but it's also not something you really need to stress about, because we have a function that can coerce timestamps, most timestamps that are any at all sane, into good index keys. So that's what this dates to array function is. I'll talk about the details in a second here, but the gist of it is this view is sorting all the documents by their timestamp, but it's translating the timestamp format into something that is more amenable to grouping. So you can see that the keys here look like year, comma, month, and that's because we're at group level 2. But if we turned reduce to false, or turned the group level to infinity, or said group equals true, so we group by unique keys, what you'd see is that those timestamps go all the way out to the second resolution. So it could be 2010, comma, November, comma, 14th, comma, 10 p.m., and however many seconds. And it's the date to array function that's a built-in helper in the MapReduce runtime that you can use to translate sort of arbitrary timestamp formats into these keys. So on the lower right-hand corner, you see, sort of 1970, February 18th at, 5 p.m. and some odd minutes and seconds is that timestamp there. So once you've built an array of value, of numbers like that, now you can group, on 1970 or on February or on the day or on the hour or the minute or the second. And this lets you do some, some fun graphing. The other thing it lets you do is not have to write the code to convert timestamps into those arrays in the first place, because getting that right is just a tiny bit tricky, and it's just easier to call date to array to get your key. So with group level 2, as we saw earlier, we're getting monthly results, but we can also get hourly or daily segments. So with group level 3, we're getting daily results, and with group level 4, we would get hourly. And what this is really great for is for statistical, sort of analytic, lightweight analytic browsing and queries. So if you want to find, what hours of the day are most popular for a given tag, or you want to, figure out how much traffic you're getting to a particular URL and graph that over time, this is a great way to do it, and to have those graphs kept up to date in near real time incrementally. So another query pattern that's going to be, useful and is popular among our users is a leaderboard. You want to find the users who are winning the game, or in this case, we want to find the top-rated beers. So part of this is going to impact on your schema, right? If you want a leaderboard, you want to be able to sort something, by this value, so you can get the things where the value is the highest. In this case, what we've done is we've saved the ratings for a given beer on the beer document itself. We could do something where the ratings are independent documents and then we group them by the beer ID, and but what you end up having to do then is 2 passes over the result set. So if you want to handle a leaderboard, with the built-in MapReduce and not have to run an additional sort of sorting step in your application code, this is the way you do it. You stick what you want to sort by on the thing you want to sort. So in this case, we want the average, sort of top rating. So let's look at what the view to do that looks like. So you've got here a view that, if the document has ratings, the ratings are all stored in that sort of top-level hash map to ensure that a given user only has, can only rate each beer once. So if the document has ratings, well, we'll start out with 0 ratings and a total rating of 0, and then we'll loop through all the ratings and count them and add up the total. And when we're all done, we can come up with the average and use that for the sort key. So we'll see, it looks like the Honey Pilsner wins with the lowest rating of 2.6. We could switch the query options by clicking, so if you guys see my mouse there, this is a screenshot, but if you were to click this triangle, it lets you, make the queries into a descending sort, and that will show you the highest rated beer instead of the lowest rated beer. So this code here, there's a few lines of code, but what it breaks down to is just calculate the average rating out of that data structure and use it as the sort key. I'm going to just go back and peek at that data structure again. So here's the rating, and you can see I rated it a 5. We have some other ratings on here, and so all the information you need to calculate the average lives in the document that you want to put on the leaderboard. So you can see how, like, maybe if these documents were players in your game and every time they finished a match you stored the score on their profile, then you'd be able to easily find the players who, had the highest average score, as well as the players who'd played the most games, etc. So yeah, with that, if there's any additional questions, I'm happy to take them, or also please do email me at jchris@couchbase.com or tweet to me at jchris, and we can take any questions you have offline too. All right. So yeah, thanks everybody, and we'll look forward to seeing you at future webinars.